Hello, everybody. My name is Karsten, and welcome to the first part of our Kea DHCP webinar series. Today, it's all about the fundamentals of DHCP. So today, the stuff is not directly about the Kea DHCP server or any DHCP server. The stuff we learned today is generic DHCP. We will dive into the Kea DHCP then in the next webinar. So what we will have is a short history of DHCP. Then we talk about how DHCP version 4 works, which is the DHCP version for IPv4. And then we look what's different in the IPv6 world with DHCP v6. And at the end, we have some references, books, websites, RFCs, according to the topic. So what is DHCP? It's short for Dynamic Host Configuration Protocol. It's one of the most fundamental protocols for the internet, especially for company networks and home networks. It is a protocol that is there to assign IP addresses and network-related configuration to TCP/IP-enabled machines. Here we have a short history of the DHCP protocol, including the most important dates when the ISC DHCP server, the older open source DHCP server from ISC, has been developed, and also Kea. So it all started back in 1993 when the initial DHCP v4 RFCs were published. Then a few years down the road, there was the ISC DHCP release 3.0. which was I would say, the first one, which was really feature complete in the sense that it would be widespread in use. Then 4 years later, DHCP version 6 came along, the DHCP version for IPv6. And then ISC DHCP started getting support for that DHCP version 6 in 2007. In 2010, the development of the new DHCP server started. And that was because the code base of the older ISC DHCP got too old. It was something that had to be renewed, and it needed a fresh start. The version 1.0 of the Kea DHCP was then released in 2015. And the version 1.8 has just been released a few weeks ago. And in 2018, we have seen a big overhaul of the DHCP v6 RC, where the good people at the IETF collected all the interims RC that updated the standard and put that all into one document, so that if today we want to understand DHCP v6, there's one larger document that contains it all. Let's have a first look on DHCP v4. We have in DHCP v4, we have clients, which can be directly wired connected clients with Ethernet. They are usually connected to some networking device, a router or a switch, and that networking device acts as a relay agent for DHCP. And then in a central place, we have a DHCP v4 server that gives out the network configuration and the IP addresses. Clients can as well be mobile clients that connect over wireless protocols. Could be smartphones, could be laptops. Of course, having just one DHCP server is a single point of failure. So most networks see multiples of them contained as a cluster. And we will, as part of the series, look into how to make DHCP servers high available with building a cluster. And Kea has especially good features for that. So if we look directly on the protocol level, DHCP v4 uses UDP broadcast and in some situations also unicast. And the server and the relay agents, they listen on UDP port 76. 67, sorry. And the clients themselves also listen on a port, which is port 68. They listen for messages coming from the server or from the relay agent. The tricky part in IPv4 is that in order to use DHCP, the client needs to talk to the server, but the client doesn't have an IP address. So it can't talk IP, because in order to talk IPv4, you need to have an IP address. So the tricky thing here is that for the initial request, a client requires layer 2, which is today Ethernet communication. And also the server side needs to be able to receive that request from the client. DHCP is an upgrade from an earlier protocol called BootP. And the big difference between BootP and DHCP is the lease concept. In BootP, configuration and IP addresses had been given out forever. There was no way to put a timestamp on the IP address given out. DHCP is different in that it has this lease concept that gives an IP address only for a limited amount of time. So a client can never keep an IP address forever. Every IP address given out by the DHCP server has a lease time, and that is the time in seconds that the client is allowed to use that IP address. Technically, the lease time is a 32-bit value, and the maximum lease time you can have in DHCP is some 4 billion seconds, which is roughly 136 years, and that should be long enough for most networks. There is a special value for the lease time, which is the decimal -1 or hexadecimal all F lease time, and that indicates an infinite lease. Now that contradicts a little bit what I said earlier, that in DHCP, no client can have an IP address forever, which is almost true except for the special lease time, but be aware that not all clients implement this. So according to the RFC that defines DHCP, a DHCP server must store the lease information on some permanent storage, usually a disk, before confirming the IP address to a client. And in order to do that, it also needs to serialize all requests. So the performance of writing back to disk, that could be a bottleneck on a heavy-duty DHCP server that gets a lot of requests at the same point of time. During the webinar, we will discuss various options to prepare for this bottleneck or even make it go away. So because a client machine without an IP address can only talk to the local link, to the local Ethernet broadcast domain, the DHCP protocol, the initial one, is link local only. But we don't want to have DHCP servers in every subnet. That would be too much DHCP servers to maintain. For that reason, we have the relay agents. And these relay agents, they listen for DHCP requests from clients. And if they see one, they take the request and send them forward towards the DHCP servers. The relay agents can be often found in network equipment like routers, but there are also dedicated software-based relay agents available. The communication between a client and a server goes through certain states. And in every state, there's a specific DHCP message that is being sent. It all starts with the DHCP discover, where the client asks, is there a DHCP server here in this network that can give me an address? If this DHCP discover is being seen by a DHCP server, the server will send an offer. A client might receive multiple offers from multiple servers. And that is completely okay from the DHCP protocol point of view. The client then selects one of the offers. and sends a DHCP request to the server that has offered that one address. And if the server at that point of time still has that address available, it will write back the lease information to disk, to storage, and then if the data is stored securely on disk, sends a DHCP acknowledge to the client, and therefore confirms that the client is allowed to use that IP address for the lease amount of time. So here we have the communication between a client, a relay agent, and a server in a graphical view. We have the client in the lower right corner. In the middle, we have a router with a relay agent. We have two DHCP servers, one on the left side bottom and one on the left side top. It starts with the DHCP discover. That is a broadcast that the client will send into the network. And as a broadcast, it is seen by any local DHCP server, local meaning here being in the same subnet. It is also seen by routers that have a relay agent configured. Such a relay agent needs to be enabled by the administrator of the router. Usually, a relay agent is not enabled by default, and it cannot be auto-configured because it needs to have the IP address, the unicast IP address of the DHCP server to forward to. In this case, the relay agent is configured and it forwards the request to the DHCP server on the top. Now we have two DHCP servers that have seen the request, and both offer with different IP addresses. They will not answer in the same speed. Usually the local DHCP server, being in the same subnet, is a little bit faster in sending the offer than the remote one. The DHCP client now has two offers, two different IPv4 addresses it can choose from, and maybe different network configurations. Now, depending on the client software configuration of the DHCP client software inside the operating system, it might choose the one or the other. For example, in DHCP client software, you can configure requirements like I only take offers that contain a DNS name or a DNS domain name for this network. If there's a DHCP offer coming without that option, we won't use that. If there are no restrictions or no requirements on the client side, the client usually picks the one that sent the fastest answer, which in our case here is the local one, the one in the same subnet. Next, the client sends out the DHCP request, telling the server, yes, thank you for offering me that IP address. I would like to take that for a certain amount of time. Can you acknowledge the lease? The DHCP server checks whether the IP address is still available. Could be that some other client has taken it in the meantime, but usually it's still available, and it confirms the lease and writes that to the disk, and then sends an acknowledge to the client. And then the client DHCP software that it runs in the operating system configures the network stack with the new received IP address. The client, while doing the DHCP dance, it goes through a defined number of states, which are init reboot, init selecting, bound, renewing, and rebinding. Now, usually you don't see these. If you just work with an operating system, that all goes under the hood. However, if you troubleshoot DHCP, it might be important to know about these states because you might see them in the log files of your DHCP server. Here we see the different states and which DHCP messages relate to each state. A client without an IPv4 address starts in the init state. In the init state, it sends out a DHCP discover, and then a server gives a DHCP offer. After receiving the offer, the client is in the selecting state. From the selecting state, the client sends a DHCP request asking for the lease to be confirmed, and a server answers with the DHCP acknowledge. And then the client is in the bound state. The bound state means we have an IPv4 address, we have that configured, and we use that address for a certain amount of time. Now, a DHCP client doesn't wait until the lease is completely run out. It will start usually after half of the lease time, 50% of the lease time. It will try to renew the lease. So it sends a DHCP request to the exact same server that originally gave the acknowledge on that IP address. And after having sent the DHCP request, it is in the renewing state. And if the server is still there, and if the IPv4 address requested is still available, we get another DHCP acknowledge and everything is good, and the client goes into the bound state again and waits another 50% of the lease time. And then it does the renewing again. And if there's a DHCP egg, it goes into bound again. So this is the standard behavior in a network. It should always go between renewing and bound. If for some reason the original DHCP server is not answering with DHCP acknowledge anymore, could be because that DHCP server has been taken out of the network. So after 3/4 of the lease time, the client goes into the rebinding state. And in the rebinding state, it will send another DHCP request, but not to one specific DHCP server. It will send that DHCP request to all DHCP servers, meaning it will send a broadcast in the network. And that is being picked up by all local DHCP servers in the same subnet, and it will be picked up by the relay agent. And the relay agents will send that off to whatever DHCP servers are configured remotely. Now, if any of the other DHCP servers in the network can confirm the exact same IPv4 address, we get a DHCP acknowledge and everything is good again. We go into the bound state again as a client, and we wait another 50% of the lease time, and then we ask that server again for renewal. If we don't get an answer from the rebinding state, that might be because all the DHCP servers have been replaced, or the DHCP server's configuration of all of them has been changed. Or it could be because this client is a mobile client and it has been moved from one wireless network to another wireless network, and it is now in a completely different network with completely different DHCP servers. And of course, in that new network, none of the DHCP servers can acknowledge the previous address. The previous address might even not be valid in this network. So if that happens, if there's no answer on renewal and there's no answer on rebinding, we go back into the init state. That means the client sends out another DHCP discover, asking, is there any DHCP server out here that can give me address? I don't mind which address, just any address would be good. And hopefully there's a server that answers with the DHCP offer, and the whole states circle starts again. Now this is the state machine, or the states that we see if a client starts without an IPv4 address in the beginning. A different situation happens if the client already has a lease, but was not operational for a certain amount of time. For example, a client machine that has been shut down or was sleeping or hibernating for a long amount of time and is woken up. So when it wakes up, it already finds a lease, and that lease is still valid. So it goes into the init reboot state, and while in init reboot, it asks for a DHCP request asking the server, I found this IP address, is this still valid? Can I still use this? And if there is a server that answers with the DHCP acknowledge, it goes directly from init reboot to the bound state. And from there, it goes through the other states again. If we do an init reboot and we don't get an answer on the DHCP request, the client will directly go into init. Or if it receives an active not acknowledge, a DHCP neg, it also then goes directly into the init and sends out another DHCP discover asking for if there are any DHCP servers out there that can help me. Now these are the different states a DHCP client can be in. One important part besides giving out IP addresses is giving out or distributing network configuration with DHCP. Because DHCP is an upgrade to an older protocol, to the older BootP, there are different types of fields that you can use to send network configuration to the client. There are the older, more fixed BootP configuration fields like next server or boot file name. And there are the DHCP v4 options like domain name servers and domain search. This can be confusing for some people that start working with DHCP because these different ways of assigning network configuration, they look very much similar, but they are treated differently in the configurations. And this is because they are from different protocols actually. From the older BootP, which DHCP has inherited, and the newer DHCP v4. We will cover some of the BootP fields and the DHCP v4 options in our next webinar. A special case in DHCP are the host reservations, because sometimes a client machine should always get the same IP address. The IP address should not be taken randomly from a pool of free addresses. It should always be the same, and it should always be only be this client machine that gets the address. No other machine should be given that address. This could be required because the machine receives incoming connections, so it needs to have a stable, well-known IPv4 address. Examples are web servers, printers, maybe a database server. Sure, most people configure these machines statically, so they type in IP addresses in the network configuration of the operating system, but it's totally valid, and also some administrators do that successfully, to give the IP addresses to these machines also via DHCP. Another reason could be that there are firewall rules, and the firewall rules work on IP addresses. So the security policy is based on that IP address. So the IP address for a certain device must be stable. To bind an IP address to a client, DHCP is using client identifiers. And in most cases, the client identifiers is the Ethernet MAC address today. In the course of the webinar, we will also learn that there are other identifiers that we could use. But most of the time, it's the hardware address that is burnt into the network card. So here we have an example of how host reservations work. Here we have a mobile client, a laptop, that has a certain MAC address, AA0102030405. And it requests via a relay agent a DHCP address. And the DHCP server has two different subnets, and each subnet has a reservation for the MAC address. And in this example here, the green subnet is the 192.168 subnet. So the DHCP server recognizes that and gives out the 192.168.1.10 address, because that's configured in the configuration of the DHCP server. The next day, the same client moves to a different office, maybe in a different city. The client has still the same MAC address because that's built in, that's burnt in the network card of that laptop. It will send a DHCP request via a different relay agent. So the DHCP server, which is the same DHCP server, recognizes that this is coming from a different network. It's coming from the light blue network. And it looks for the configuration for that network, and it finds that that MAC address is also in the subnet for that network, and it gives out a 10 address, 10.2.4.20, because that's the reservation for that client. That is how host reservations work. Another special case is the shared subnet. Now, shared subnets are something that usually only appear in IPv4, and most often the reason is that in IPv4, in order to conserve addressing space, we start with very small subnets, maybe a /24, which can have up to 254 physical machines in there. And then we figure out that, oh, we actually need more machines. We need 300 machines in there. We cannot put 300 machines in the /24 network. So we have to put another subnet into the same physical network. And that creates a shared subnet. Shared subnets are extra complexity and should only be deployed if there's really a need for it. Here we have an example of a shared subnet. In the light blue network, there are a lot of machines, and let's pretend there are more machines in there than fit in one small /24. So the administrator has configured a shared subnet inside the DHCP server. Actually, two subnets inside the shared subnets. The red one containing the 192.168.1/24 network addresses, and we have a pool from 50 to 80. We give out that IP addresses to some machines. And then we have the dark blue clients that get IP addresses from the 10 network, the 10.2.4/24 network. And the pool here goes from 150 to 180. Now, in this case, if a client requests an IP address from DHCP, it depends on which subnet in the shared subnet still has free IP addresses available. We can't predict whether the IP address will be coming from the first subnet or the second subnet. Usually that will be just given out randomly or by the first one coming in the configuration. But in this case, it's also irrelevant because both IP addresses or the IP addresses from both subnets are equal. They both work, and the client shouldn't really care which one they get. There's another use case for shared subnets, and that is if you have a network, which is one physical subnet, but you have different kinds of devices, and you want to separate these devices by giving them different IP addresses. For example, cable modem and end-user CPE devices, or printers, desktop, and mobile devices. You want to separate them into different IP address ranges or networks, or point of sale terminals and other retail infrastructure devices like digital price tags. And we could do that as well insofar that we create a shared subnet, and then in the DHCP service configuration, we detect what kind of client is requesting, and then depending on the kind of client, we will then select either the red subnet, which in this case is for general mobile devices, or we select the darker blue subnet, which is here for modem or network infrastructure devices. Exactly how you can do that that we will cover in one of the next webinars. So DHCP 6, if we look from high above, DHCP 6 works the same way as DHCP 4. We don't need to learn a lot about the structure, the basics, how that works. But in the details, it's very, very different. It's not an upgrade to the DHCP 4. It's a new protocol of its own. So the ideas from DHCP 4 has been taken over, but the actual implementation is a different one. So for example, in DHCP 4 needs to start with layer 2 with Ethernet. That's not the case in DHCP 6, because in DHCP 6, every client already has a working link local IPv6 address, which are the FE80 addresses. So every client in IPv6 already has an IP address and can start talking with IP. So it's DHCP 6 is a layer 3 protocol only. It doesn't need to do any low-level kernel trickery to send raw Ethernet frames over the network. That makes DHCP 6 easier to implement and also easier to troubleshoot. We have different ports. The DHCP 6 servers and relay agents, they listen on UDP port 547, and the clients, they are listening on 546. And we don't use broadcast anymore. There is actually no broadcast in IPv6. We use multicast, which makes it much more lightweight for the network. DHCP 6 communicates with link local multicast addresses. There is one address, it's called the all DHCP relay agent and servers addresses, which is FFO2:1:2. And when we send the request to that address, it will automatically seen by all servers, DHCP servers, and all DHCP relay agents that have subscribed to that address. And there's another which is actually not link local, but site local. It's the all DHCP servers address. And this is for renewal. So DHCP 6 has been designed to work in cooperation with routers. The router will tell the client whether DHCP 6 is being used in this network. It sends the M flag and the O flag when the client asks for the network configuration from the router. The router, in addition to M and O flag, M flag being the managed flag, telling that DHCP IP addressing is being used in this network, and the O flag is called the other flag, telling the client that we don't do IP addressing in this network with DHCP, but you can ask other network configuration from DHCP. The default gateway's address will always be retrieved from the router in an IPv6 network and never from the DHCP 6 server. So here we have a picture that shows how the communication works in an IPv6 network. We have, again, the client in the lower right corner, and it starts by sending a router solicitation, which is a multicast UDP request. And that is being seen by all the routers in the network. And the router here in this network responds with a router advertisement, telling the client, hey, I'm the router, this is my address, you can reach the internet by sending packages to me. So you can use me as a default route, and actually here are the MNO flag, meaning we do DHCP 6 in this network, and you can get an IP address and you can get other network configuration from DHCP. A DHCP 6 server, and the RC is mandating that, must always issue IP addresses randomly from the address pool. And IPv6 address pools can be really, really large. This is in contrast to DHCP 4, where some server products issue IP addresses continuously. So they, in IPv4, a DHCP server could just give out the first address from the pool, then the second address, and then the third address from the pool. And in IPv4, that's not a big deal. But for IPv6, because the pools are so large, it makes sense to give them out randomly, because that makes it much more harder for intruders to guess a certain address or to do a network scan and catch all the IPv6 addresses given out by a DHCP server. Also in DHCPv4, there's just one type of IP address that can be given out by DHCP, and that is the IP address, the only one. That it's like Highlander, there can only be one in IPv4. You can't assign 3 addresses to one client with DHCPv4. Is not possible, can only be one. In DHCPv6, that's different. We have much more flexibility here. We can assign multiple IPv6 addresses to one client, and these addresses can have different flavors. They can be from the non-temporary flavor, meaning a permanent address, and that is address that is sticky. It's like a host reservation, but just quite. It will always be given to this client if that IP address is available. Now, given that the pools in DHCPv6 are so large, they are usually billions of addresses in an IPv6 DHCP pool, chances are that the address is still free is like very, very high. And you get the situation where a same client will get the same IPv6 address for multiple years in a row. Then we have the temporary addresses, and these addresses must change on each request. And also they have a low lease time. The idea here is that these addresses will be changing all the time, and clients will be using these addresses for outgoing connections. And this is for privacy reasons. So IPv6 addresses, if they are stable, could be used for tracking people. So certain companies could just look, this IPv6 address just visited website A, and 5 minutes later it visited website B, and draw some conclusion out of this. With temporary addresses, if like the addresses change every 5 minutes or every 30 minutes or so, it's much harder to track people around in the internet. Then we can have multiple addresses. A client can request multiple addresses, not just one. A client can say, can you give me 10 addresses, please? And the DHCP server can be configured either to allow or deny that. And then we have prefix delegations, which is like multiple addresses, but in a special case. Prefix delegation is usually where the client is itself a router, and it has another subnet to provision. So the router, being a DHCPv6 server itself, can request one or more whole network prefixes from an upstream DHCP server. And that allows for an hierarchical DHCPv6 configuration where the administrator in the optimal case just needs to put a manual configuration on the highest tier DHCP server, and everything down will trickle down and will just auto-configure with prefix delegation. DHCP is not the only way to give IP addresses to clients in an IPv6 network. There's also stateless automatic address configuration, also called SLAC. And SLAC can either be used as an alternative to DHCPv6, or it can be combined with DHCPv6. So you can decide as an administrator whether you want to have DHCP or SLAC or both in your network. And there are 2 different ways to get an IPv6 address for an IPv6 enabled devices. One is called the stateless configuration. The other one is called the stateful configuration. In a stateless configuration, the IPv6 address is not coming from DHCP, but it's coming from the router using auto configuration, hence SLAC. Only the non-IP configuration, like the DNS resolvers, the domain name, maybe the network time source, that is then coming from DHCP, but not the IP address. We name it a stateful configuration, when the IP address as well as the other network configuration will be coming from a DHCP server. Still, even in a stateful configuration, there can be slack. And the client will then have multiple IPv6 addresses, one and more from Slack and one and more from DHCP servers. So back to our picture here. Our client has learned that this network is DHCP v6 enabled. So it sends a solicit to the network, which is a multicast UDP, asking for, is there any DHCP server here that can give me an IPv6 address? And this is being seen by a local DHCP v6 server and also by a router with a relay agent. And the router does a relay forward to a remote DHCP server. The local one, the local DHCP server, answers with an advertise. The remote one answers with a relay reply to the relay agent. And then the relay agent takes the data from the relay reply and creates an advertise, which is the same kind of advertise that the local DHCP server has been sent. Both is unicast UDP. It's not broadcast, it's not multicast, because we already know the link local address from the client. So we can directly do IP communication here. The client, again, selects one IP address, or based on the configuration, one set of IP address and configuration, and then sends the request, again, direct unicast UDP to the DHCP server. And the server replies with an DHCP reply, which is similar to an acknowledge, telling the client, yes, you can use that IPv6 address. And then the client configures the new IPv6 address in the network stack. Because in IPv6, the client can have multiple addresses, we have the idea of an identity association. And that is required in order to be able to reference a specific DHCP IP address being given out. So if a client has multiple IP addresses and maybe even got that IP addresses from different sources, from a router, from one DHCP server and maybe from a second DHCP server, there must be a way to identify these IPv6 addresses with their meta information, like where did they come from, lease time, and so on. And that is the identity association. As a user, you won't see that, but as an administrator of a DHCP v6 server, you might stumble upon this identity association. And it's a way to, on the server side, separate the different IP addresses and configurations given out to the same client. And we have different identity associations for temporary addresses and for the non-temporary addresses. Similar to a DHCP v4 client, a DHCP v6 client goes to different states. And here the states are very much the same in the order and the how they are used than in DHCP v4. They are just named differently, and also the messages that are leading to the state transitions are differently. So we start in the init state, and the client sends out solicit and gets an advertise from the server and ends up in the selecting state. And then client sends out the request, server sends a reply, and we are in the bound state. Now this is, again, the default state, or not the default, the standard state of a client. It has an IPv6 address, one or more, and it can operate with that address. And after 50% of the lease time, it tries a renewal. So it sends a renew message. And if we get a reply telling us everything is good, we can use that lease for another lease amount of time. We go back in the bound state. If we don't get that reply from our server, we ask for a rebind. And then we go in the rebinding state. And if there's any server in the network that can confirm the IP address that we already have in use, we go back in the bound state. If there's no answer, or if there's a negative answer on renewal and rebinding, we go back to the init state. Now this is very much the same as we have seen that in DHCP before. This is the bird's eye view that is still the same, but the internal implementation, the kind of messages that flow on in the network are different. DHCP 6 knows one special way of giving IP addresses to clients, and that is called rapid commit. And the idea of rapid commit is to speed up the process of joining a network. For example, a mobile handset, a smartphone, if that goes into sleep, it might shut down and give up the IP address. And when it wakes up, it then needs to reconnect to the wireless network. And users expect that the client is immediately usable and can talk to the network. Rapid commit can help with that. So with rapid commit, there is no information sent to the DHCP server that the client is actually using the advertised IPv6 address. In rapid commit, the client asks for an address, one or more servers advertise an address, and then the client just uses one of the addresses without telling the DHCP server that this address is in use. This means that the DHCP servers must always reserve all the addresses that they advertise, even if they are not in use by clients. This is not a problem because the network sizes in IPv6 are so large. Again, we have billions of IPv6 addresses in one subnet and in the pools that this doesn't create any problems. So here we have a picture with rapid commit. So the client starts with a solicit asking for an IP address. That solicit is being received by 2 DHCP servers, and both servers answer with a reply. And the client now just selects one address, either the one from the local DHCP server or either the remote one. And the remote or the local DHCP server never will get an information whether the client is really using the address they have advertised. So both servers then need to mark the IP address as being in use for the least amount of time. So this concludes DHCP v6, and now I have a few references, books, and recommended web pages. Unfortunately, first are RCs before I say unfortunately. So these are the relevant DHCP v4 RCs, and there's one big RC for DHCP v6 that should contain everything that is DHCP v6. That one is just recently, a few years ago, being published, and it collects all the original RC, and it's an overhaul of the original RCs for DHCP v6. So unfortunately, DHCP is not a topic that publishers really like to invest money in. It seems to be. It's a niche, so there's not so much choice of DHCP books. The classic book is the DHCP handbook by Ralph Dromes and Ted Lemon. Both Ralph Dromes and Ted Lemon, they work in the IETF working groups, and they actively, even today, work on the DHCP, both DHCP 4 and DHCP v6. But that book is over 20 years old. It is still relevant from the generic idea of DHCP, but the world has changed a lot since 1999. Then there's the book from Tim Rooney, IP Address Management, Principles and Practice. And this covers the broader idea of doing IP address management, but it contains DHCP and some ideas of how to manage DHCP. There's the TCP IP guide, which is from 2005, also not very new, but still it explains how DHCP works. And the Windows Server 2019, which is the newest book I have in this list, covers the Windows sides of the world, and especially the Windows DHCP server and how to configure that. And for the websites, there's of course the excellent documentation of the Kea DHCP server. There's the ISC knowledge base with tons of good stuff in there. The TCP guide, which is the free version of the book, is there that you can use. And also Microsoft has some basic information on DHCP. And of course, this being the first part of our webinar series, here you see what's coming in the next webinars 2 weeks from now. We have installation and configuration of the Kea DHCP server. And then on the 14th of October, we have lease allocation, client classification, and option assignments. After that, we look into high availability and the database backends, very interesting stuff. 18th of November, we have monitoring, logging, and Stork, which is a graphical user interface for Kea DHCP. Currently, mostly for monitoring and logging purposes, but it will grow and will get more functionality over time. We will showcase that. And on the 2nd December, the last installation of this webinar, we will talk about migrating from the older ISC DHCP to the new Kea DHCP and some best practices in doing that. And being there, do we have questions?
Yes, I was just typing the answer for one of these questions. Someone was asking about the recording. This has been recorded and it will be posted on the ISC YouTube channel and also linked to the ISC website under community and presentations. So one of the questions that we have is, what is the difference between a shared subnet and a VLAN?
Yeah, a VLAN is an extension to Ethernet, and it separates it creates two virtual Ethernets on the same physical infrastructure. But from the network's point of view, it's two different Ethernets that are there and two different collision domains. So on the Ethernet side of packages, the different VLAN packages, they don't see each other. And a shared subnet, it's just one Ethernet. So if you do sniffing with a tool that is not VLAN capable, you still see the packages from all the clients. And the clients are not separated in any way from each other than using different IP addressing space. And because they're using different IP addressing space, they can't directly talk to each other, but they can sniff each other. So if you start a TCP dump on one of the clients having a 10 address, that client can still sniff the other clients having the 192.168 addresses. So it's still the same Ethernet layer. In a VLAN, you can't really do that because you shouldn't be, at least from without having a sniffer that is VLAN capable. So yeah, VLANs are really separating the packages, while shared subnet is just two networks overlaid on a physical Ethernet. Hope that explains it.
Yeah, it's a complicated question. We have another question. How is FE80, the linked local address, assigned on a DHCP v6 client?
The FE80 addresses are being created from the prefix FE80, and then the last 64 bits of the address are created from the MAC address. So the operating system, when booting up, will identify the network cards, and it will read the MAC address from the network cards. And an Ethernet MAC address is 48 bits. So we are missing 16-bit to get full 64 bits that we need. So the operating system will stick the hexadecimal numbers F and FE in the middle of that MAC address, actually creating two parts. And with that extra 16 bits in the middle, we have now a 64-bit number. And that is the later part of the IPv6 address. And then we put FE80 in front of it. And that creates a full link local IPv6 address. And because MAC addresses must be unique, at least in the same subnet. I know that there are network cards out there that have the same MAC address because some vendors, they messed up. But usually these network cards shouldn't be in the same subnet, else Ethernet communication wouldn't work. So because we have all different MAC addresses, we all have different link local addresses, and the machines can directly communicate in the link local network with the FE80 addresses.
Okay, we have a couple of other questions. One, Stephen is asking, for someone completely new, would you recommend incorporating the Stork server right from the start? We are going to cover that later on in the series. You know, you'll get an introduction to the Stork server. The Stork is a separate project. It provides a monitoring, a web-based monitoring utility for Kea. It doesn't configure the DHCP server for you, it just monitors it. So if you need a monitoring solution, yes, it's pretty easy to use. We provide you with a Docker image or a package for your OS. Another question, yes.
Vicky,
Yep.
for a similar question, if someone has asked us whether to start now with either Kea or ISC DHCP, I would say don't start today with ISC DHCP. If you don't have an existing installation, start with Kea because it's a more modern and a more future-proof solution.
Right, so that actually was the next question was, what are the major differences between Kea and ISC DHCP? I don't know if you address that next week or not.
Yeah, I will address that next week, but I can peek a little bit into that. First of all, it's more modern in the design insofar that it scales better on modern architectures, on more modern server machines than the ISC DHCP. It directly supports and has built in from the beginning with database support, which is an important feature there. You don't have that in ISC DHCP. It has been built in with modularity and extensibility, so it has these hooks. Not every function needs to be in one monolithic system. The ISC DHCP is a monolithic system, so every function needs to be in there, and you maybe can select a function during compile time. But if you get the ISC DHCP from your Linux distribution, it has mostly all the functions enabled, even if you don't need them. In Kea, it's more modular. You can have plugins that you can load or unload during runtime, and you can select that you need certain features and you don't need certain other features. That makes it more lean, and also it reduces the attack surface from the security point of view. And the last thing is that it has also been designed from the beginning to be to have an API, and I mean a real API, not OMAPI, which some people have experienced to be not so nice to work with, which is the API from the old ISC DHCP. Kea has a nice modern REST API. You can use web tools, and if you have developers or if you are a DevOps that have been working with REST APIs that the other players in the industry use, you feel right familiar with working with Kea and automatically like provisioning Kea with the API or requesting information from there. But we will dive deeper into the differences next time.
So we have another question, and this may also be a better question for next time, asking whether or not Kea supports containerization. And I'm not sure if this is a question about Kea particularly or about, what formats we provided in.
I can say that I've deployed Kea in Linux containers, both Docker/Podman or systemd type containers, and it works quite well. So from the technical point of view, yes, it can be deployed and it works in containers. Okay.
We don't actually have a published official Docker image for Kea, and the reason is honestly, we looked at whether or not we wanted to take on responsibility for vulnerabilities in the operating system that we built on, and at the time we decided not to do that. But so that's more about how do we distribute it versus what can you do with it. One last question. For those people using IPv6, do you recommend DHCP or is Slack enough?
That actually depends on the kind of clients you have in your network, because the situation currently is in this way that if you have Microsoft clients, so Microsoft operating systems or Microsoft devices, they require DHCP6. They support Slack, but they support Slack not in the full feature set that they can work with only Slack. So you need DHCP6 for them. On the other side, Google's Android devices, or general Android, might it be from Samsung or Huawei or whatever, whoever is selling Android devices. Android devices don't support DHCP6 at all. They require Slack. And then there are the Apple devices that happily do both and do that quite right. So it really depends on what kind you have. If you're a purely Microsoft shop, then DHCP6 is enough. If you do Android and only Android, then Slack is enough. If you have Mac and Apple devices, you can choose. Most people have all of them, so they need to implement all of it. I'm sorry, that's the way the world is.
Yeah, I would just add that a year or so ago, Cricket Lou posted a blog that I thought was really good on the Infoblox website addressing that question. And as I recall, kind of the upshot of his message was that if you want the control and the visibility that you get in DHCP, the people in the enterprise are always going to want that level of control and visibility. It's a bit harder to have visibility into Slack, given that it's, you have routers handing out addresses all over the place. Anyway, that is it for the questions. We do have somebody asking if you have any reference on the fact that you mentioned that Microsoft clients require DHCP v6. I think you meant vis-a-vis Slack, but somebody's asking if you have it.
Not at the moment. I think I can find something there, and we can maybe post that with the slides.
Okay. All right. Well, thank you. We've run over by 9 minutes. Quite a few people have hung on. I thank you very much for this, and I hope we see you next time. That will be in 2 weeks.
Thank you, everybody. Have a good day.
All right. Bye-bye.